this discussion, we will talk about how to write Taylor polynomials for mathematical functions. Taylor polynomials. A Taylor polynomial of a function f of x is a polynomial function that approximates f of x on an interval centered at some value of x, say x equal to a. The nth degree Taylor polynomial of Pn of x for f of x at x is equal to a is Pn of x equal f of a plus f prime at a x minus a plus f second derivative of function f of a at a divided by factorial 2 x minus a squared plus the third derivative of f of x at a divided by factorial 3 x minus a to the third power, and so on until we reach at nth derivative of f of x at a divided by factorial n f of x minus a, x minus a to the nth power. So let me call this expression as expression A. The proof of this expression is beyond the scope of our discussion today. Therefore, we will not focus on the proof. However, we will focus on how to write Taylor polynomial to some known functions, such as f of x equal e to the x, f of x equal ln of x, and so on. So let's consider an example. Let me call that example at example 1. Let's say this is the question. Write the Taylor polynomial of f of x equal e to the x about or at x is 0, and we try to get maybe, let's say, 4th degree Taylor polynomial. So that means I'm not going to extend our discussion beyond the 4th degree for this example. We will have examples later on talking about more than 4 terms or 5 terms. Since we are looking for the 4th degree polynomial for f of x, that means we are looking for p4 of x. Now if we use expression A on the previous page, we should be able to write p4 of x equal f of 0 f prime at 0 x plus f double prime at 0 divided by factorial 2 x squared plus f triple prime at 0 divided by third factorial plus f fourth derivative divided by fourth exponential 4th factorial, and so on. So let me call this as expression 1. Now to obtain this, only thing you have to do is to use the expression on the next page, which is, I call it expression A, and plug in x is equal to 0, a equals 0, and n equals 4. Now we need to find all of those derivatives. F of 0 is in fact, f of x is in fact e to the x. That's the function that we are trying to find the Taylor polynomial for. Then if I find the first derivative, f prime of x is going to be e to the x. As you know, whatever order that you get derivative for, e to the x is always the derivative of e to the x is always e to the x. So I could simply write fn of x is e to the x. So if I plug in x is 0, that's what we are looking for. So fn at 0 is always 1 because e to the 0 is in fact 1. So this expression is valid for all n as long as n is a whole number. So if I substitute this from in expression 1, I will have p4 of x equal 1 plus f prime of 0 is 1. So we have x plus f double prime at 0 is also 1. So 1 over factorial 2 x squared plus 1 over factorial 3 x to the third. Sorry, I did not write x to the third power there. So factorial 3 x to the 3 plus 1 over factorial 4 x to the fourth power. So if you want, we can even write this expression as 1 plus x squared over factorial 2 plus x to the third power over factorial 3 plus x to the fourth power over factorial 4. Now, before we go and try to convince you that this is an approximation to e to the power x, now this function that I have wrote is supposed to be approximately equal to e to the x at around x equal to 0. So what I'm going to do is to convince you that this expression is valid. I'm going to make up a table for you to let you know how the values of e to the x and the polynomial function that I have derived, I'm talking about this particular function, differs for each some values closer to x equal to 0. So let me say I have some x values here, and this second row will tell you if I evaluate the expression that we have found. I'm talking about this expression p4 of x at those x values, and let me evaluate e to the power of x on the last row. Now let's say if I say x is negative 0.5, using my calculator I found out the value of p4 of x is 0.60677, whereas e to the x is 0.60653, and if I put, let's say, negative 0.3, I get 0.74084, whereas e to the negative third power is 0.74082. Of course, if I put 0, both values are going to be 1. If I put, let's say, 0.2, I get 1.2214, and this is also 1.2214 up to 4 decimal approximation. Now if I put 0.3, 1.3498, and this is 1.3499. You can see that the fourth decimal number a little bit different for 0.3. Now if I go, for example, to 0.5, my answer will be a little bit off. However, close to 0, you can see these values are so much equal to each other. So what we are saying is we could use this polynomial expression, which is p4 of x, to evaluate e to the x if you are looking for answers, let's say, about 3 or 4 decimal numbers. So let's talk about another example. Let me call it example 2. The question is, find the fifth order Taylor polynomial for f of x equal ln of x. So this is the function that we like to write Taylor polynomial for at fifth degree at x is 1. Now if we use the expression a, so let me write a and substitute a equal 1 and n equals 5, so I will obtain Pn of P5 of x. So if I write with these two substitution, I will have P5 of x equal f of 1 plus f prime at 1 times x minus 1 plus second derivative of f of x at 1 divided by factorial 2 x minus 1 squared plus f the third order derivative of f of x at 1 divided by factorial 3 x minus 3 squared x minus 1 to the third power plus fourth derivative of f of x at 1 divided by 4 factorial 4 x minus 4 to the x minus 1 to the fourth power plus f fifth derivative divided by 5 factorial times x minus 1 to the fifth power. So this is the Taylor polynomial for the function f of x at fifth degree. Now only thing we had to do is we should find the derivatives of the functions. So let's say we know f of x is ln of x. So if that is the case, f prime of x is 1 over x, and f double prime of x is, with a little bit of manipulations, you should be able to tell me that is negative 1 over x squared, and f the third derivative of x, f of x, is 2 over x cubed, or rather I could write that as factorial 2 over x cubed. Then if I go for the fourth derivative, this is negative factorial 3, or rather it will be 6, but I am writing that as factorial 3 divided by x to the fourth power. Now we also need the fifth derivative of x. This is supposed to be positive, 24 divided by x to the fifth power, which is same as factorial 4 over x to the fifth power. Now if I evaluate these expressions at x equals 1, that's what we need. So we put f of 1, definitely ln of 1 is 0. Now f prime at 1 is 1 because x is 1. F double prime at 1 is negative 1. Now if I go to f third derivative of f of x at 1 equal factorial 2, because we are plugging in x is 1. So f fourth derivative of f of x at 1 equals negative factorial 3, and the fifth one at 1 is factorial 4. So you can see right away there is a connection between the derivative and the answer. So substituting this value in expression 1, let me call this expression 2 because that's what we are looking for. So if I substitute these values here, I will get P5 of x equal, first term is 0, f1 is 0, so let me write 0 anyway, 0, 1 times x minus 1, minus 1 over factorial 2 x minus 1 squared plus factorial 2, which is f third derivative of f of x at 1 over factorial 3 x minus 1 to the third. We have two more terms, so plus, sorry about that, minus factorial 3, which is this number right here, divided by factorial 4 x minus 1 to the fourth power. Finally, the last term plus factorial 4 divided by factorial 5 x minus 1 to the fifth power. So if we simplify this expression on the previous page, I have p5 of x equals x minus 1 minus x minus 1 squared over 2 plus x minus 1 third power over 3 minus x minus 1 to the fourth power over 4 plus x minus 1 to the fifth power over 5. In fact, if you like to write a general term for this expression, which is y equals ln of x. So if I express this using the series notation, I could say Pn of x equals sigma n equals 1 to, or k equal 1 through n, negative 1 to the power k minus 1 over k, x minus 1 to the power k, although this is not required for this particular question, but I thought it's worth mentioning it to you so that whenever you need the 6th order or 7th order or 7th degree Taylor polynomial for ln of x, you could use this expression to find that. Finally, let us look at another example. I am calling that as example 3. Now let's go for the general term. So we are looking for Pn of x for f of x equal, let's say 1 over 1 plus x at a equals 0. Sorry, x equals 0. In other words, x is in fact equal a is 0 here. So if I substitute a equals 0 in expression A on the first page I will have Pn of x, and also I need to plug in x is 0 also. So Pn of x same as f of 0 plus f prime of 0 x plus f double prime at 0 over factorial 2 x squared f third prime over factorial 3 at 0 definitely x cubed, and so on until we get to fn at 0 factorial n x to the n. So let me call this as expression 3. Now we need to find out derivatives for f of x. So f of x we know it's negative 1 plus x. And f dot prime of x, with a little bit of using either quotient rule or some other ways, we could find f prime of x is negative 1 over 1 plus x squared. I'm not going to illustrate how to find the derivatives of these functions, but however, if you know a little bit of calculus, you could easily find derivatives. So f double prime of x is supposed to be 2 factorial, or rather 2 over 1 plus x squared And if you go on finding the derivatives, you might be able to find out if nth derivative at x is in fact negative negative 1 to the nth power of n factorial divided by 1 plus x to the nth power. So if I evaluate these functions f of x at 0, we need the values of the derivatives at 0. So f of 0 is definitely 1 over 1, which is 1. And f prime at 0 is negative 1. F double prime at 0 is factorial 2. And in fact fn at 0 is negative 1 to the power n factorial. So if I substitute these values in expression 3 will tell you then Pn of x equals f of 0, which is 1, plus f prime of 0 is negative 1, so we will have negative, x plus f double prime is factorial 2 divided by factorial 2 x squared minus factorial 3 divided by factorial 3 x cubed, and so on until we get to a situation it says n minus 1 to the nth power n factorial divided by n factorial x to the n. So this is simply equal to 1 minus x plus x squared minus x cubed, and it's going to alternate the signs, and the x to the exponent gets further increasing. So final term will be negative 1 to the power n x to the n. So if I have to write 1 over 1 plus x in polynomial format, it might look like 1 minus x plus x squared plus minus x cubed plus x to the 4th power, and so on. So depending on the approximation that you need, you can evaluate 1 over 1 plus x in polynomial function. For example, let's say let me say my x is 0.1. So what I'm looking for is 1 over 1 plus 0.1. So if you express this in polynomial, Taylor polynomial, this is supposed to be equal to 1 minus 0.1 plus 0.1 squared minus 0.1 to the 3rd plus 0.1 to the 4th power, and so on. So it should be 1 minus 0.1 plus 0.01 minus 0.001 plus 0.0001, and so on. So this will allow us to estimate 1 over 1 plus 1, which is 1 over 1.1, in decimal form. Depending on the decimal numbers that you need, we can stop this series notation wherever we want or terminate our process. So as a final note, all we need is a function f of x which is differentiable indefinitely or to any power any times, and if you have a function as such, we should be able to express that function as a polynomial function. As you know, it is easy to evaluate polynomial functions than any other trig functions or log functions. So it has lots of benefits. Whenever you express a function, let's say trig functions or transcendental functions, where you may need a calculator to find the answers, for example sin x or cosine of x or something of that nature. And if I had to evaluate these functions at a given values, it might be easier to use polynomial expressions to approximate the values of these functions, not only sin x, cos x, or any other functions, at any given value.